we are looking at the Rayleigh-Schrodinger perturbation theory, and just by way of recapitulation of the notation, let me put down here what exactly we had stated. We were looking at the non-degenerate case. I will discuss the degenerate case later. By degenerate I mean that the energy has a g-fold, the energy eigenvalue is g-fold degenerate. So, here we have the non-degenerate case, and we had a total Hamiltonian which was h naught plus lambda h prime. There was a discrete spectrum, and the eigenfunctions, the energy eigenfunctions were represented by psi n 0 and the corresponding energy eigenvalues by E n 0. And then because of the perturbing Hamiltonian h prime, the total wave function had this unperturbed form plus lambda psi n 1. And you could stop here if you were looking at the first order in the perturbation, or you could continue and get to the second order in the perturbation and so on, depending on the context, because you should decide where exactly it makes sense to truncate the series. Similarly, the energy eigenvalues get a contribution because of the perturbation. To first order there was a contribution E n 1, to second order there was a contribution E n 2 and so on. And then we had these expressions. We were looking at first order perturbation theory, and then we had the contribution to the first order of the energy was the matrix element of the perturbing Hamiltonian in the 0th order state, psi n 0. And then we had a very crucial expression, the contribution to the wave function to first order. That means just the first order contribution, I am neglecting the 0th order contribution, was summation over k not equal to n psi k 0 h prime psi n 0 by E n 0 minus E k 0. It is good to pause here and understand what exactly this matrix element means. Now, look at the numerator. The matrix element there is the transition matrix element. H prime takes this state psi n 0 to psi k 0, and we can in short form call that H prime subscript k n. So, transition matrix elements become extremely important in general, and it is after all the perturbing Hamiltonian which is responsible for taking us from one state to another state. So, let us look at an example and see what this means. The example that I am going to take is from optics. I have an atom interacting with a radiation field. The atom has discrete levels, could be a 2-level atom, 3-level atom, anything, but these are the atomic levels. I am looking at a situation where not only is the atom a quantum object with discrete energy levels, but the radiation field is also quantized. Now, normally in a situation where the atom interacts with the radiation field, a very popular perturbing Hamiltonian. The perturbation is because the radiation field is affecting the atom and is going to provide atomic transitions. Because of the perturbation, the atom could jump from a higher level to a lower level, releasing photons, or it can go from a lower level to a higher level by absorbing photons from the radiation field. And H prime, a common example of H prime is minus d dot E, where d is the atomic dipole operator and E is the electric field. Now, the atomic dipole, like all dipoles, is going to be represented by the charge E times R, and I am looking at a case where E is spatially homogeneous. Now, this is a reasonably good approximation. It is called the dipole approximation because the atomic dipole interacts with the radiation field, and E itself is taken to be spatially homogeneous over atomic distances. In other words, the size of an atom is typically of a few angstroms, and I would assume that if I use light, electromagnetic waves with wavelength of the order of about say 500 nanometers, then across the size of the atom, across a stretch of a few angstroms, I do not expect the electric field to change terribly. So, the electric field is taken to be independent of space. It is a constant field. The vector sign is because there is a polarization vector E naught times I have quantized the electric field. And if you go back to one of our discussions a long time ago, where we were using the harmonic oscillator model, the linear harmonic oscillator model, to describe quantum optics, we realized that the energy density for the electromagnetic field is E squared plus B squared, apart from constants like permeability, permittivity, overall factors and so on. Somewhat similar to the quadratic Hamiltonian that you have in the case of the harmonic oscillator, which is essentially x squared plus p squared, give or take some constants. And then we used the ladder operators of the harmonic oscillator, and we wrote the electric field as A plus A dagger, A minus A dagger, and therefore the magnetic field as A plus A dagger. This is apart from some constants. So, the constants become irrelevant here. Perhaps I can even absorb the constants in E naught. So, E naught has the polarization vector and some overall constants, and I have A minus A dagger, where A is the photon destruction operator, A dagger is the photon creation operator, and there is no time dependence here. So, the perturbing Hamiltonian has no time dependence. The polarization vector is the vector quantity here. So, there is a dot product between the dipole, which has vector r, and this. There are operators here, and those are the A's and A daggers. So, these are the operators relating to the radiation field A and A dagger, and this is the dipole operator, if you wish, corresponding to the atom, because it is the atomic dipole. Now, in a situation like this, what is it that I will have as far as the matrix elements of H prime go? Basically, I am looking at the matrix elements of D dot E, because that is the perturbing Hamiltonian. What are the initial states? Let us imagine that the atom is in an initial state, is initially in some state A, or I if you wish, that is the initial state of the atom, I A. In my notation, the suffix A means an atomic state, and the field has n photons initially, and therefore, the state of the radiation field is n. So, my initial state would be I A direct producted with n. Now, this goes to a final state, which is a final state of the atom. Now, two cases are possible. The final state could have been reached by absorption of photons by the atom. Let us say it absorbed one photon, and therefore, the photons in the radiation field, at least one of them was used up, and I have a final state which is given by F A. Clearly, this is a higher energy level compared to I, because the radiation field has lost a photon, and that photon has been absorbed by the atom to go to the state F. Now, this is one possibility. The second possibility is where the initial state of the atom becomes the final state F, but that is because the atom emitted a photon and went from a higher state to a lower state. The photon itself gets absorbed by the radiation field, and while I had initially n photons, it now becomes n plus 1. So, these are two possibilities, but I only talk about going from one state to another of the atom by absorption of a single photon or by emission of a single photon. Now, this process corresponds to absorption. The atom has absorbed a photon, and this corresponds to emission of photon by atom. This is absorption of photon by atom. So, these are the possible processes that I have. So, if this is my initial state and that is the final state, let us look at case 1. How do I go from one to the other? So, the matrix element is essentially the atomic dipole operator taking an initial state I of the atom to a final state F, and then of course, I have a matrix element which is essentially A minus A dagger coming from the electric field, taking me from an initial state n in the first case to a final state n minus 1. Let me call this as the matrix element dFi, and here I am with this object, but A on ket n gives me root n ket n minus 1, and since the photon number states are orthonormal to each other, that gives a contribution. The second term, that is A dagger on ket n, takes it to n plus 1, and that does not therefore make a contribution. So, I have this, and this is the term H prime psi n psi k, or the transition element contributions that come from H prime in the case of absorption. Absorption of photon by atom. Clearly, this makes sense. Suppose I switched off the radiation field, That means there are no photons to be absorbed. So if n is 0, this term drops out. That is common sense. If there is no energy pumped into the atom, there is no way by which the atom can absorb energy and move to a higher state, and therefore such a transition is not possible. So that is okay. Now you look at the second case. Once more I have the atomic dipole operator's matrix element dFi, and then there is a situation where the radiation field initially had n photons and finally had n plus 1 photons because the atom emitted a photon. Now what is this quantity equal to? This is dFi. A on ket n is root n minus, it gives me ket n minus 1, and therefore that does not make a contribution. But A dagger, forget the signs, A dagger produces a root of n plus 1, ket n plus 1, and this is 1, and therefore I have, apart from signs, constants and so on, I have a root of n plus 1 times the atomic part. Now this is a very important point. It tells us that even if you switch off the perturbation, even if there are no photons supplied by the radiation field, you switched off the radiation field, that means you set n equals 0, you still have emission of photons by the atom. Clearly this is a very spontaneous emission of photons, because the atom spontaneously emits photons without the usage of an external radiation field. This is a purely quantum mechanical phenomenon. You do not have a classical counterpart for spontaneous emission. It therefore becomes a very interesting feature of quantum physics. So if n is 0, you have spontaneous emission of photons by the atom. If n is greater than 0, it is clear that the radiation field stimulates the atom to emit photons, and that would be stimulated emission. Spontaneous emission, as I said, has no classical analogues or classical counterparts, and that is a very interesting example of time independent perturbation theory, where I have used the fact that the energy levels are not degenerate, because I have chosen energy levels where the initial state has a certain energy and the final state, although energy is conserved, each state has a different energy. So F has a higher energy compared to I, and so on. So this is a very interesting example of non-degenerate stationary perturbation theory. The next thing I wish to discuss is degenerate perturbation theory. Now look at the expression for psi n1. In the denominator, suppose there is degeneracy and En0 equals some Ek0, the denominator blows up and the perturbation formalism as such will not hold unless the transition matrix element in the numerator is also 0. How do I alter this formalism to take care of the degenerate case? Clearly trouble comes in the first order contribution. So I go about it in the following fashion. Let me take an example. Right now not an example from physics, but let me look at a situation where there are 3 states, psi 1 0, psi 2 0 and psi 3 0. Let's make kets out of them, and let's say that psi 1 0 and psi 2 0 correspond to the same energy value. So I have H naught psi 1 0 is E naught psi 1 0 and H naught psi 2 0 is also E naught psi 2 0. On the other hand, let us imagine that psi 3 0 is an eigenstate of H naught with a very different energy eigenvalue, such that E 3 0 is not equal to E 0. So, in this problem there is a twofold degeneracy. The degeneracy is here. Corresponding to the energy value E 0, there are 2 independent, linearly independent states, psi 1 0 and psi 2 0. These are normalized states, they are orthonormal to each other. In that case, I could do the following thing. The trouble does not come from here. The trouble comes from here because in the denominator, in the first order contribution, E 1 0 minus E 2 0 is 0. The way to handle this is by working in this space of degenerate states. Here I have twofold degeneracy, and whatever I say is extendable to G-fold degeneracy, G being as large as you wish. So, I could define 2 objects, phi 1 0 and phi 2 0, which are linear superpositions of psi 1 0 and psi 2 0. So, let me say that this is S 1 1 psi 1 0 plus S 2 1 psi 2 0, and I have a phi 2 0 which is another superposition S 1 2 psi 1 0 plus S 2 2 psi 2 0. These 2 states are taken to be orthogonal to each other and they are normalized states. So, S 1 1 squared plus S 2 1 squared is 1, S 1 2 squared plus S 2 2 squared is 1. So, these are normalized to unity. What are the requirements that I have of these 2 superposed states? The requirements are the following: phi 2 0 H prime phi 1 0 must be equal to 0. The reason is the following: H naught acting on phi 1 0 is H naught S 1 1 psi 1 0 plus S 2 1 psi 2 0, and that is the same as E 0 phi 1 0. Similarly, H naught phi 2 0 is also E 0 phi 2 0. So, instead of looking at psi 1 0 and psi 2 0, if I worked with these combinations phi 1 0 and phi 2 0. So, in this example k and n can only take values 1 and 2, and of course, psi has to be replaced by phi appropriately. And now, since the denominator becomes 0, the matrix element in the numerator should also be 0. So, this is certainly a requirement. I expect phi 2 0 H prime phi 1 0 to be 0, and therefore, its complex conjugate phi 1 0 H prime phi 2 0 here to be 0. In general, if there is a G-fold degeneracy, I certainly expect phi k 0 H prime phi n 0 to be 0, where phi k zeros and phi n zeros, the phi's happen to be linear combinations of the original G-fold degenerate states. Then what happens? Suppose I work with phi 1 0 and phi 2 0, it is clear that E 1 1 has to be of course computed in the unperturbed basis, but now we have for the degenerate states the unperturbed basis states to be phi 1 0 and phi 2 0. So, E 1 1 is phi 1 0 H prime phi 1 0 and E 2 1 should be phi 2 0 H prime phi 2 0. So, this is essentially what I need, and the aim is to not just find out these energy values which are hopefully different from each other. We also need to find these states, which means we should be able to fix S11, S21, S12 and S22. Of course, if I worked with G-fold degeneracy, I should have G different energy values, each of them being the element, matrix element of H prime with respect to the appropriate linear combination of the original states. And in that case, I will have G of these, G linear combinations, and I should work with them. And I will demand that H prime phi k phi n, where k can take values 1 to G and n can take values 1 to G. In this case, if k is not equal to n, I demand that that is 0 in order to carry out my perturbative calculation. So, in order to do this, it is best to illustrate it with an example. This is essentially what I wish to do. My example would be a perturbed hydrogen atom. So, let us look at the perturbed hydrogen atom. As you know, the hydrogen atom, the energy levels except the ground state, the energy levels are degenerate, and the perturbation which I will use in the first order perturbation theory, you find that a very interesting effect comes about. It is called the linear Stark effect, and the degeneracy is lifted at least in some sector, and we will see what that is. So, we will use the perturbed hydrogen atom to demonstrate what I say. So, the Hamiltonian has a free part. I am going to set lambda equals 1 and a perturbation. Now, this free part, this is what I have. This free part, the hydrogen atom problem, we had earlier on reduced it to an effective one body problem, and H naught is minus H cross squared by 2 mu, where mu is the reduced mass, del squared, we work in spherical polar coordinates, minus Z squared by R. So, that is the unperturbed part of the hydrogen atom. I need to provide a perturbation. The perturbation could come in the form of an electric field. I am going to consider an electric field. The perturbation has the electric charge E times an electric field, and this electric field is going to be modulus of E times Ez. It is a homogeneous field, it is a constant field. So, this is what I have. Clearly, I need to compute matrix elements. I need to first of all decide what level I am looking at. You will recall that in the hydrogen atom problem, the wave functions of the hydrogen atom carry with them 3 quantum numbers, n, l and m, So, the generic wave function is psi n L m, and for convenience we could work in spherical polar coordinates. So, I have psi n L m r theta of r theta phi. The degree of degeneracy is given by n squared. You will recall that n takes values 1, 2, 3 and so on. So, when n is 1, there is exactly one state corresponding to the hydrogen atom, and that is the ground state. However, when n is 2, for a given value of n, L takes values 0 to n minus 1, and for a given value of L, m takes values minus L to plus L in steps of 1. These you will recall from our earlier discussion of the hydrogen atom. So, if I take n equals 2, there are 4 states corresponding to this energy level. So, there is a degeneracy, and these 4 states I can represent them by psi 2, L taking value 0 and therefore m taking value 0, L taking value 1 and therefore m taking value 0, or 1 or minus 1, because m takes values minus 1 to plus 1 in steps of 1. So, there is a 4-fold degeneracy, and these are the various wave functions, each of them being a function of r theta and phi, corresponding to the first excited state of the hydrogen atom. This is the first excited state. We are interested in the matrix elements of H prime, the matrix elements which therefore connect various initial states out of these to various final states. The typical matrix elements would be the following. I need to consider, so if I am looking at the off diagonal elements of H prime, I need to consider psi 2 0 0. Suppose I started with psi 2 0 0 and I did this. This object is going to correspond to the energy to first order, and that is 0. 0 for the following reason, because as you can see, this is the first order contribution to energy. Take the unperturbed wave functions and find the expectation value of H prime in that state, and that should give me the first order contribution. So, the first order contribution to the state is this object, but H prime is E modulus of E times E z. I can well refer to this as vector E. This is an electromagnetic process, and electromagnetism conserves parity. The electric field itself is a vector, and therefore it changes sign under parity. These wave functions, the angular part of the wave function, in general psi n L m of r theta phi, in the case of the hydrogen atom, has a radial part given by r n L of r and an angular part given by y L m of theta phi, and this is the object that tells me that every eigenstate, energy eigenstate of the hydrogen atom has a definite parity given by minus 1 to the L. So, returning to this quantum number is L. This has even parity. H prime itself has the electric field E, which changes sign under parity. So, this whole object is a state with odd parity, but that has even parity. And since electromagnetism is electromagnetic interactions are parity conserving, this object has a first order contribution which is 0. Similarly, if you look at psi 2 1 1 for instance, H prime psi 2 1 1, the same problem, except that this state has odd parity because L is 1 and this also has odd parity. So, this entire state has even parity and that has odd parity. So, corresponding to the state 2 1 1, the first order contribution is 0. Similarly, for all these 4 states as it stands, the first order contribution is 0, and therefore, if I find out the first order wave function, remember that that has a numerator by a denominator which is En 0 minus Ek 0, summation over k not equal to n, and note that the numerator itself has matrix elements multiplying wave functions. And since all these 4 states have the same energy, there is a problem unless the numerator becomes 0. So, let us look at the numerator. The numerator has the off diagonal elements of H prime. So, basically if I have a state here, I should put in another of these 4 states on the other side. So, in the numerator, as we know, there are matrix elements multiplying wave functions. Let us not worry about the wave functions, we look at the matrix element at this point. So, let me look at an element like psi 2 1 0 H prime psi 2 0 0. As it stands, the parity operation allows this. This has even parity, with this whole object has odd parity and this has odd parity. So, indeed I have a problem, because in this expansion there is a term psi 2 1 0 H prime psi 2 0 0 by E 2 1 0 0 minus E 2 0 0 0. This is 0 and this is non-zero. I am putting down just one term in the summation, and there too I have not put down the appropriate wave function that multiplies the matrix element, but this will do for my discussion. So, I do have a problem if I work with psi 2 0 0 as my initial state or with psi 2 1 0 as my initial state. Now, you would think at the face of it that the same problem will persist if I have this. Look at this matrix element. As far as the parity argument is concerned, this would be non-zero, because this has even parity, the whole thing has odd parity, and this has odd parity. So, it is fine. However, if you take these terms in and do an integration, the answer is 0. You would find the following. Let us look at psi 2 1 1 H prime psi 2 0 0. Look at the angular part of the wave function. This is y 0 0 of theta phi. This H prime contributes just z, which is cos theta, and psi 2 1 1 has a y 1 1 of theta phi, and this object has to be integrated. Essentially, this amounts to integrating this over d omega, like psi 2 1 minus 1 H prime psi 2 0 0, that too is 0. So, these two terms turn out to be 0. So, as far as the state psi 2 0 0 and psi 2 1 0 are concerned, the problem does not come from elements which involve psi 2 1 minus 1 and psi 2 1 1, but this is the non-zero element. So, this is where the problem is. Now, if you look at a state psi 2 1 1 and see what are the transition, what are the matrix elements of H prime. So, let us look at that. If I started with the state psi 2 1 1, and I looked at all possible final states which are different from it, we have already shown that this is 0. This too is 0 because of parity arguments, and this too is 0 because of parity arguments. Similarly for psi 2 1 minus 1. They do not seem to have any problems because are not on the same footing as the S state term and the P state with m equals 0. So, you may imagine that these are really the analogues of the phi's that I wrote earlier. In other words, you do not need to consider superpositions of psi 2 1 minus 1 and psi 2 1 1, and you could do the first order perturbation theory with no problems as such. So, let us look at these two states, psi 2 1 minus 1 and psi 2 1 1. What is it that I have? In the first order of perturbation, if I look at the state psi 2 1 1 and its energy eigenvalue contribution, what is it that I have? Unfortunately, this cannot connect these two states. So, the energy contribution is 0, parity arguments. And then if you look at the first order contribution of this form, by similar arguments, the first order contribution of energy is 0. So, even to first order, although the numerators that I was talking about, although they vanish, it turns out that the energy eigenvalues are the same and the degeneracy is not lifted. Let me retrace my argument. I found that the numerators in the first order contribution to the wave function were 0, and therefore, there was no need to look at superpositions analogous to the wave function phi that I was talking about earlier. However, look at the energy eigenvalues. The energy eigenvalues are 0 because the physics of the situation does not let the Hamiltonian H prime connect have non-zero matrix elements, diagonal matrix elements of this kind. And therefore, the degeneracy as far as these two states are concerned, the degeneracy is not lifted in the first order. You have to go to the second order in order to worry about how the degeneracy is lifted in this case. In general, if it is not lifted in the second order in any general context, you will have to move to the third order. It is quite possible that the degeneracy persists to large orders. However, in this problem at least, while these two states, there is no point thinking that the degeneracy would be lifted in the first order. It does not happen as I have just now shown. It turns out that as far as these two states are concerned, I can produce superpositions of psi 2 0 0 and psi 2 1 0, two linearly independent states orthogonal to each other, such that they have different energy eigenvalues and they satisfy all the requirements of states that I expected from superpositions of the degenerate states. In other words, as far as first order perturbation theory is concerned, the degeneracy between these two states is lifted because I will define a phi 1 0, which is some S 1 1 psi 2 0 0 plus S 2 1 psi 2 1 0, And I will also define a phi 2 0 which is S12 psi 2 0 0 plus S22 psi 2 1 0 such that these states are normalized to 1, and my demands are the following: phi 1 0 H prime phi 1 0, which is the contribution E 1 1, is not equal to 0. Phi 2 0 H prime phi 2 0, which is again the first order contribution to the other state, is not equal to 0, and above all phi 2 0 H prime phi 1 0, this is 0, because after all if I were to calculate the first order contributions to the wave functions, it is this kind of term that is going to sit in the numerator, and in the denominator of course I have E 0 minus E 0, because we have already seen that this phi 1 0 and phi 2 0 are eigenstates of the unperturbed Hamiltonian with eigenvalue 0, and therefore the numerator should be 0. So these are the three conditions that I have to impose. The aim is to determine the first order contribution to the energy from both these states, as also the wave functions, which means we need to determine these coefficients S11, S21, S12 and S22. This is going to be done by diagonalizing H prime in the phi basis, finding the eigenvalues and the eigenvectors, a matter which I will discuss in further detail in the next lecture.